Look at a standard bridge or an airplane wing and you will see a geometry of straight lines, right angles, and perfect circles. This is the language of human engineering, a way to simplify the chaos of the world into something we can calculate by hand. But if you look at a tree root or a bird's wing, that Euclidean geometry disappears. Nature rarely uses a straight line. Instead, it uses a complex, often messy-looking logic that we are only now beginning to understand and translate into our own machines. A hawk can dive at speeds exceeding 200 miles per hour, yet its skeleton is remarkably light. For a long time, we thought bird bones were simply hollow tubes. But if you cut one open, you see a delicate, chaotic-looking web of thin struts called trabeculae. This internal lattice isn't random, it is concentrated exactly where the stress is highest. By placing material only where it is strictly necessary, nature achieves a strength-to-weight ratio that puts our solid steel beams to shame. It is a lesson in doing more with less. The idea of looking to nature for flight isn't new. Leonardo da Vinci spent years filling notebooks with sketches of bird wings, trying to mimic their feathers. His machines failed because he focused on the appearance of the bird rather than the underlying physics. He wanted to build a mechanical bird, whereas modern bionics seeks to build an efficient wing. Today, we are moving past simple imitation. We are no longer making machines that look like animals. We are using the same mathematical rules that animals use to survive and thrive. In traditional engineering, we often use overbuilding as a safety net. If we aren't sure how much stress a bridge will take, we make the beam thicker. This adds weight, which requires more support, creating a cycle of inefficiency. Nature cannot afford this. Every gram of extra weight in a bone requires more energy to move, which could mean the difference between life and death. Because of this, evolution has refined structures that are legal by traditional manufacturing standards, shapes that are too complex to be easily carved or cast in a mold. This is where modern software enters the picture. We are now using generative design, a process where an engineer gives an AI a set of constraints such as the load a bridge must carry and the points where it must be anchored. The software then grows a solution. Instead of a standard truss, the result often looks like a system of roots or coral. These designs outperform human blueprints because they aren't limited by our aesthetic preference for symmetry. They are purely functional, placing matter only where the physical forces of the world demand it. Consider a bridge designed this way. From a distance, it might look fragile, even alien. There are no clear horizontal beams or vertical pillars. Instead, the structure branches out, distributing tension and compression through a web of interconnected filaments. If you were to remove one part of a traditional bridge, the whole thing might fail. But like a spiderweb or a tree canopy, these bionic designs are redundant. They can sustain damage in one area while the rest of the structure compensates, mimicking the resilience found everywhere in the biological world. In the world of aviation, we are seeing a shift away from hinge flight. Currently, airplanes change direction by moving flaps, mechanical parts held on by heavy hinges. But a bird doesn't have hinges, its entire wing warps and twists. Engineers are now developing compliant mechanisms, single pieces of flexible material that can change shape without any moving parts. These wings are lighter and far more efficient. By eliminating the gaps between flaps and the wing, we reduce drag and fuel consumption while mimicking the smooth, organic motion of a soaring bird. Something as humble as a blade of grass offers a masterclass in structural engineering. A skyscraper must be rigid to withstand the wind, but if it is too stiff, it can crack under extreme pressure. A blade of grass survives a storm by being flexible. It uses a hollow, reinforced shape that allows it to bend nearly 90 degrees without breaking. Engineers are applying this logic to high-rise buildings and wind turbine blades, creating structures that work with the forces of nature rather than fighting them with brute, unyielding force. The reason we haven't built like this before isn't just a lack of imagination, it was a lack of capability. It is nearly impossible to forge a steel beam that looks like a tree branch using traditional factory methods. However, 3D printing has changed the rules. We can now print complex, lattice structures in metal and carbon fiber that were once impossible to manufacture. We are finally entering an era where our manufacturing tools are as sophisticated as the designs we find in nature, closing the gap between the rigid machine and the organic organism. As we look to the future, the distinction between a machine and an organism may continue to blur. Our bridges will grow like roots, our planes will flex like wings, and our buildings will breathe like skin. This isn't just about aesthetics, it is about sustainability. By using nature's illegal designs, we can build a world that uses less material, consumes less energy, and lasts longer. We are finally learning that after 4 billion years of research and development, nature might just be the most advanced engineering firm on the planet.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.